Hi, this is question 2 from the AQA Further Pure for June 2009 exam paper. In this question, we're asked to write down the 3x3 matrices which represent the transformations A and B, where A is a reflection in the plane y equals x, and B is a rotation about the z-axis through the angle theta, where theta is equal to pi over 2 radians. So that's a quarter of a turn. Now, if we start off thinking about part A, so for part A, for the first part of part A, we're trying to find a reflection in the plane y equals x. So if we think about our identity matrix, which I've got here, and I'm just going to move that over there, and we have a reflection in the plane y equals x. So what's happening there is our y and our x are swapping over, they're swapping places, and we can think of it in that way. So our y coordinates will become our x coordinates, and vice versa. So if we, on our identity matrix, if we simply swap the y and the x around, so that first column was the x and the second column was the y, then this here will be our transformation matrix. So any point that I multiply this by, any position vector that I multiply this by, the x and the y of that position vector will swap places. So this is a reflection in the plane y equals x. So I'll stick that there as our answer for that. Okay, for part 2, it says B is a rotation about the z-axis through the angle theta, where theta is pi over 2 radians. So rather than go through the theory of this, I'm going to just have a quick look at our formula booklet. But before we have a look at that, because it's a rotation about the z-axis, that's telling us that the z-axis is going to be invariant, so none of the points on the z-axis would move if you rotated about it. So we already know that our matrix for part 2, I'm going to put in the first bit because we know that we are going to have this here. That bit is going to stay the same because that bit's going to be invariant. Okay, so if I have a look at our formula book, so this should be on one of the pages in your formula book, and it's saying that the matrices for rotations in 3 dimensions through the angle theta about one of the axes are given by these here, and we've got something that's, I'll just get rid of that. We've got something that's about the z-axis, so it's this one here that we want to be using. Okay, and we already decided on that part of it there, so all we need to do now is we need to put in pi over 2 for each of these components here. So the cosine of pi over 2 is going to be 0, and that's going to be 1, that's going to be -1, we've got 0 there. Okay, so this matrix here gives us our transformation matrix B. Okay, just going to tidy up a little bit, let's get rid of that. Okay, part B says find the matrix R which represents the composite transformation A followed by B. Now it's worth remembering that when we're doing A followed by B, what we're actually going to do now is we are actually going to multiply B, find the product of B and A in that order. Okay, so we reverse the order in what we find the product. So So for part B, first part of part B, R is going to be equal to, and because it's A followed by B, we're going to do B, I'm going to times that by A. And I'm just going to write those out. So this was our matrix B over here. So we're going to have 0, 1, 0. Okay, and it may be worth you pausing the video now and just having a quick go at doing this yourself. Okay, so because we've got a 3 by 3 matrix multiplied by a 3 by 3 matrix, so any square matrices that we multiply together, then our answer to this is going to be a 3 by 3 matrix. Our result's going to be a 3 by 3 matrix. Okay, so what I'm going to do is I'm going to use my I'm going to use my arrows again to guide me as I do this. So I'm going to have row 1 times by column 1 first of all. So that part there is going to be 0 times by 0, which is 0. And then I've got negative 1 times by 1, which gives me negative 1. And then I've got 0 times by 0, which is going to give me 0. Okay, so that's going to be the first bit. And in fact what I'm going to do is I'm just going to do this part a little bit quicker. You might want to have a go at finishing this off yourself now, and I'm just going to go ahead now and I'm just going to pop in the answers. The first one will be negative 1, and then I'm going to have over here, I'm going to have row 1 column 2, so row 1 column 2, and that's going to be 0, 0, 0, and then we've got row 1 column 3, and that's going to be 0, 0, 0 again, and then we've got row 2 column 1, so we're going to have 0, 0, 0 again, that's going to be 0, and I'm going to just pop in the rest of the answers, so that's 1, 0. And there you go. So that's going to be the matrix R, which represents a transformation A followed by transformation B, and we did B times A to work this out. Okay, part 2 of this is asking us to describe the single transformation represented by R. Now if we have a look at this over here, what I can see is that the Y and the Z are invariant. Okay, so I've got an invariant plane there. The YZ plane is going to be invariant, and my X coordinate is becoming negative. Yeah, so any X coordinate that I've got, if I multiply by this transformation matrix, the X part component is going to become negative. So what that tells me is that this is a reflection in, and we can either call it a reflection in the YZ plane, or I'm going to call it a reflection in the plane X equals 0. Okay, there you go. Thanks very much for joining me.